Hello again. As I said in the previous video, as I was finishing up there, I said that we can use the differential delta y, and that was a typo there. Oops, typo, something I miswrote. This should have been dy. I'm sorry about that. So we can approximate our exact change in our function, that's delta y, by the differential dy. So another use of differentials is to approximate errors that are resulting from measurements. So let's recall a few types of errors. First of all, we have an absolute error. So this is the measure of the difference between a measured or approximate value and the exact value of a quantity. So in other words, the absolute error would be equal to, in magnitude, the approximate value minus the exact value. The relative error is a way to express the error in a measurement or an approximation as a proportion of the exact value. So normally we would say that the relative error is the absolute error, and this can be in magnitude, but it doesn't have to, because absolute error is already in magnitude. And then we would divide by the magnitude of the exact. Now the problem is, when we're talking about measurements, we don't have the exact value a lot of times. So we take that and we approximate it by the measured value, or by the approximate value. So we take our absolute error and we divide it by our approximate error. And then the percentage error is a way to express the error in a measurement as a percentage of the true value. So that's going to be the relative error times 100 to get a percentage. Now the way that this relates to differentials is, if we go back to absolute errors, if we notice that often we don't have what the exact value is. So we have to approximate the absolute error some way. And the way that we do that is by using the differential. So the absolute error is going to be approximated by dy. Now the reason for this is partially because of what I said on at the end of the previous video. If f of x is close to L of x, then that's going to mean that the exact error is close to, or the exact change in y is close to what the differential dy is. Now the error is, let's see if I can, there we go. The error is this amount. The change is, the change in f of x is that amount, and let me do one more. The dy value, the differential value, is this whole amount. So clearly there's some differences there, but if all of these values are small, then saying that the error, let me go back to here, is approximately equal to dy is not a terrible approximation. Perhaps there might be something better, but if you don't know what the exact value is, then this is about all you have. So we say the absolute error then is approximately equal to dy. So if we take that then and use it in the relative error, we can say that the relative error is approximately equal to dy divided by the approximate. And then of course we can use that in our relative error to get dy divided by the approximate value times 100 to be an approximation for the relative error. And these are the formulas that we're going to use when we work through number 3, but I will do that in a separate video.